Better? Or do we need to close? Actually, why are the windows open? It's a little bit chilly, huh? Dasha, before you sit down, can you close those two windows, please? Yeah. Thank you. Nice, he kept the name in it. I told him to call it that.
What's it called?
Yeah, that's the database. I was modifying my code last week to make sure it'll work because I realized when I made the database originally, I only designed it to have one user. So I have to, I better double check, but it should be okay. Yeah, no, I have to double check before Friday. What? We'll talk before. Well, we'll talk more before Friday, but it's just bring your laptop to it. I'll show you a couple of examples of what to do. Then you can put on your headphones and work away.
Okay.
It's just copying and uploading, you know. So once you see a couple of examples of how to do it, then we'll just work away on it. And then after the database is done, you can be thinking about what type of worksheets or what way you want to access the database. You know, like do you want to just pick a topic or multiple topics, or you know, have a think about how you would like to access it. I can't remember. Colin, I think, has his by type, is it? Or topic, is it? He picks a topic and then you get all those topics, is it? Yeah, for that topic.
It'll show what year it was.
Yeah. Yeah, okay, Grant. Okay. So look, what I did with the other group, which I'd like to do with you, is I wanted to get the course finished today, and we didn't have our class today. So, because I think he has an EAP writing exam or something. So I thought, well, I'll make the tutorial the class, so that way we can have semester 1 finished, and then starting tomorrow, then we're just doing revision. Okay? So I thought the best thing would be just like get this last topic finished with, and then we can go ahead then with revision. Okay. Have we got everybody now?
Yeah.
3, 4, 8. Yeah. Okay, you ready, guys? We'll have a look at the last topic here. So the last thing we want to have a look at in probability for semester 1 is probability trees. And probability trees work really well when you have a series of AND events. So what I mean by this is you have an event A followed by event B and then event C and so on. You understand what I mean here? By like a chain of events. Okay. So I will give you an example of a probability tree, and we'll have a look at some calculations for this. Okay. So let's say we're looking at the events of tomorrow. And we check the weather forecast, and we are told that there is an 80% chance it will rain, and therefore a 20% chance it will not rain. Rain, not rain. You can appreciate that your chances of being late for school depend on the weather. Okay? So, for example, if it will rain tomorrow, then the probability of being late, we could say, is 0.7. And then of being not late would be it has to be 0.3. And then late and not late again. So this here we could say is, let's say, 0.2. And here we could say probability of not being late then would have to be 0.8. So if it rains, what's the probability of being late? 70%. And if it's not raining, 20%. Seems reasonable. So the advantage of the probability is that we've kind of created two worlds. Do you get what I'm saying? We created two scenarios, two worlds. We can look at a world in which it'll rain tomorrow, and then a world in which it will not rain tomorrow. And let's see how we can calculate probabilities. So let's start off with an easy one. The probability that it rains tomorrow. Well, that's no calculation involved. What's that? 80%. Okay, a little bit harder now. What is the probability that it'll rain and you will be late? Well, the way it works in probabilities, as my good friend will tell me over here, ands mean you multiply, and ors mean you plus, yeah. So, rain and late would be 0.8 times 0.7, which is 0.56. Yeah, I hope. Okay. Let's do one a little bit harder now. What about if I said to you the probability that you'll be late tomorrow? Well, here there are two ways to be late. You can be late because it's rain and you're late, or it wasn't raining and you're late. So let's just write that out. That's the probability of rain and late.
Plus.
Yeah, plus or not rain and late. So as you said, that's a plus. That's 0.87 times 0.7 plus 0.2 times 0.2. And that works out to be 0.6. Yeah? Okay?
Yeah.
So you add up all the paths to give you the outcome that you want. In this case, being late. Yeah? Okay. The next formula, I'll have to look at the proof of it. It's quite short on the side here. Suppose I ask you something like, what's the probability that it rained, given that the person is late? Now, we've looked at these before, but in the lesson with probability tables. Okay, so we need a formula here, which we'll work out on the side. Do you remember the meaning of this symbol? Given that? Yeah. So let's go back for a moment to when we had the probability tables. Let's say you have two events. You can get A or not A. And then you can have B or not B. And let's put in some numbers. Letters, rather. So let's just call whatever numbers here A, B, C, and D. And this one will be the total number of B's. Let's call that N1. And here, the total number of not B's. We'll just call it N2. What goes here? Total number of A. And then not A's. And then this guy here is the total of everything. So I'll call that capital N. Now don't be put off by me not using numbers. Okay, so this is just like the example of male, female, tea drinkers, not tea drinkers, or whatever. Okay? How did we calculate something like this? Probability of A given B. What went on the bottom here? Correct, N1. The total number of B events. And on the top?
A.
Small a. Yeah. Now watch this trick. I'm going to divide the top and bottom by capital N. So I've changed the top into a probability and the bottom into a probability. What probability is represented by small a over big N? A and B. And what is represented by N1 over big N? B. So do you see what we've done? We've actually proven a rather simple formula. The probability of A given B is the probability of A and B over probability of B. That is the conditional probability formula. Now you don't need the proof, but you definitely need the formula here. So if you can write that down. Okay, you got that proof? The formula. So if I go back here, I can now answer this question. What is the probability that it rained, given that you know for a fact the person was late? Rain and late over late. So rain and late we worked out earlier as being 0.56, and late we also worked out as being 0.6. So I think this is 0.93. 93 recurring. So, if somebody came in here late, then there was a 93% chance it rained. That's what you're saying here. Yeah? By the way, if there's a 60% chance of being late, what is the probability that the person is not late? 40. And that's using the not rule. Probability of A is equal to 1 minus not A. Yeah. Or, as you already understand it, the total probability must be 1. Yeah. Can I scroll down? Yeah, you sure? Yeah. Now, I'll give you an example just to see if you've got a handle on it. So, you have 3 boxes, and you mix the boxes up so you don't know which one you're going to get. So you could get box A, B, or C, but you don't know. In the box A, there are 3 red, 1 green, 2 red, 2 green, and then finally in box C, 1 red, 3 green. So your tree looks like this. First you pick a random box, and then you take a ball out. And so it could be red or green, red or green, red or green. Yeah? What's wrong, Dasha? No, it's okay? Can you see okay? Do you understand the simple little game? You pick a box, and then you pick a ball out of the box. That's it. So I have 3 questions here. First one is the probability of getting a red. Second one is the probability of getting a green. And the third one is the probability that you actually selected box A, given that you got a red. Okay, give those a calculation. Say again?
Did you cancel this green marker?
I'm not sure. This A here?
Oh, no.
A.
Talking about the 3. Like, it looks as if you used the green markers like cancel it.
Ah! That's the mute symbol. Is that what you're talking about? Yeah, watch what happens if I do this. Yeah, that's why I have it on mute. There now. All better? Got it? Okay, so probability of red should be 1 over 3 times 3 over 4 plus 1 over 3 times 1 over 2 plus 1 over 3 times 1 over 4, and this equals 1 over 2. Right?
I don't know where's the 3 coming from. Yeah.
Where's the 1 over 3 coming from? Because you've got to choose a box, A, B, C.
Oh.
Yeah?
Yes,
Yes, yes. Yes. What is the probability of getting green? A half, yeah, because green just means not red. Yeah. Probability of box A being the box you picked. Well, that's A and red over red. So I know the denominator is a half and the numerator is 1/3 times 3/4. So this is a half then.
For the first two parts,
Yeah.
I'm getting 0.495.
What?
I use decimals.
Ah, you have your answer, so. Because your 1 over 3 was being rounded to 0.33.
Yeah. Will it be wrong if I?
Yes. For probability trees, they kind of expect you to use fractions. Okay, write that down if you didn't get it. Now I have an important example to do next for another quote. Example. Fine, because 1 over 3 is in common, so you can take it out. Yeah, that's fine. Yeah. The which one? The 3 over 4 is because in the first box you've got a 3 in 4 chance of getting red, because there's 3 reds in 4 balls. So. Okay, do you have that written down? Yes? Scroll down. Now, I'm going to give you 2 pieces of vocabulary here. Well, actually, before I even talk about that. So, here is a biology question. A person, for example, a person takes a pregnancy test and the result of the test is positive. Is the person definitely pregnant?
No.
Good answer. So you all understand naturally that just because a test comes back as positive isn't meaning there's a 100% chance that that's a true result, right? Maybe you even talked about this a little bit in biology with testing for the presence of an enzyme or a protein or whatever, okay? Anyways, we have this vocabulary to quantify how good a test is, right? What's wrong? Huh? Okay. Anyways, you might think we use a word like accurate, but actually we need to be more precise than this. We talk about a test, how sensitive the test is and how specific the test is. So let's say you're testing for the presence of some disease or whatever it is. The sensitivity of the test is the probability that you get a positive test result given that the disease is present. Do you understand? So how sensitive a test is the probability the test will give you the positive test result given that the disease is present. So in other words, somebody has the disease and they take the test. What's the probability that the test says they have the disease? you would hope that this number is nearly 100%, right? There we go. So with that in mind, what do you think might be the meaning of how specific a test is?
How much of the thing is contained?
Oh no, it's going to be similar to this. When the disease is not present,
Oh.
probability that the test result is negative. And again, you would like this number to be nearly, no, in this case, nearly 100. Yeah, because you want it very likely to have a negative result when you don't have the disease. So just to be crystal clear, let's have a look at just the events here. So firstly, the person either has the disease or they don't have the disease, right? Then they either get a positive result or they get a negative result. And if they don't have the disease, they either get a positive or a negative result. Now, from the medical test point of view, this is a good outcome in the sense that the person has the disease and the test came back as positive. So this is a good result. What else is a good result of the 4 outcomes here? This one down here, isn't it? They don't have the disease and the result is a negative. This is a good result in that the test did its job. But these two are bad. The first one here is called a false negative. They have the disease, but what were they told? They don't. And this one here? False positive. They were told they have the disease, but they don't. Of the 4 outcomes, which is the worst? False negative is the worst outcome. Why is a false positive not so bad? Yeah, there'll be follow-up, won't there? There'll be follow-up appointments and tests and all that. So, worse outcome. This is worse. Worse compared to this one, and certainly to the other 2. Okay. So, I don't know. Have you talked about this in biology, or? I think Colin might have mentioned false negative and false positive. So you have an idea that this does happen in real life. Okay. So let's put some numbers in to give an example. Okay. So let's make the disease not too common. Let's say it's a 0.01. So it's a rare disease. Well, relatively rare, I suppose. And so the probability of not having the disease? 0.99. Okay. Now, how good would we like our test to be? So, you have the disease. How likely would we want the test to say that you've got the disease? Oh, let's go higher.
90.
Oh, let's make it 99. Okay. And then, for here, being given the all clear when you don't have the disease, let's also make that 99. So, what number goes here? You have the disease and 99 and 0.01, and here this one is 0.01 and this one here is 99. Okay. Right, can I scroll to the side for a second before we continue with this? Yeah? I'll go back to this in a moment. I just want to paint the picture here, right? So look. Here's the trolley. Here you are sitting on it. Okay, and here's the doctor coming back now. Let's put the stethoscope around the neck as well there. Okay. And the doctor's coming back with a positive test result. And the doctor's delivering this news to you. And you say, okay, break it to me, doc. How good is this test? The doc says 99% sensitive, 99% specific. Does that mean you definitely have the disease if it's positive? No. But we would like to know if you have the disease. So precisely what is the probability that the patient would like to know? Not that they have the disease or not, but rather that they have the disease, given that they know something already. What is it that they know? That the result is positive. You see, if I just said, now wait a second, if I just said, what's the probability of having the disease? Well, what is the probability of having this disease in the general population? Yeah, 1%, isn't it? Although that's a very different question. What's the probability of having the disease if you have a positive test result, isn't it?
Yeah.
That is definitely not going to be 1%. So what I'd like you to do is calculate for this patient here. They've just gotten a positive result back and they want to know what is the probability that they have the disease given that it's a positive result. You will have to use the formula from earlier, the conditional probability formula. Nope. That's what David said in the last class. So you must have made the same mistake he made.
1.
1.
No.
Someone else made a similar mistake in the last class.
0.5.
0.5 is the answer. What's on the numerator?
0.5.
What term? Probability of disease and positive. And in the denominator? Positive. So disease and positive would be 0.01 times 0.99. And positive would be 0.01 times 0.99 plus 0.99 times 0.01. And you get 0.5.
Teacher, will this come out in the exam?
I've seen stuff like this in the semester 2 exam. They don't usually throw you such a tricky one in the semester 1 exam. So, if we go back to our patient in the waiting room, what is the probability that they have the disease? 50% chance. That doesn't seem so hopeless now for them, does it? Right? 50-50. Oh, okay. Now, what is causing this rather strange result? I mean, the test looks good, doesn't it? 0.99? Looks good, doesn't it? Guys, 0.99 looks good, doesn't it? Doesn't seem to be much wrong with the test. I mean, yeah, okay, we could do better, but it seems like it's good enough to begin with. It is this number here. If I was to change this number, let's say I made the disease 5% of the population, and this here is 95%, then how do the numbers change? It would be 0.05 times 0.99 over 0.05 times 0.99 plus 0.95 times 0.01. If I just change this to 5%, then this probability, instead of being 0.5, will become 0.84.
But teacher, why 0.99?
The test is still... I'm not changing anything about... I'm not changing the physical test. The test is still just as good. All I'm doing is changing how many people actually have the disease in the population.
Right.
So instead of saying 1% of people have the disease, I'm now saying 5% of people have the disease. What has happened to my result here? The patient now has an 84% chance of having the disease instead of 50%. Now I hope this is making you think. Have I changed anything about the test? Nothing. Is the test just as good as before? Yeah. But somehow the risk to the patient is significantly different now, just because of the change in the population. This is quite strange. It means population itself has some bearing on how good or bad the test is. It's not simply just how good or bad the test is. It's also how prevalent the disease is among the population. Maybe you wouldn't have thought this to begin with. You maybe said, well, what difference does it make? It's either how good the test is or not. Do you get what I'm saying?
Yeah.
Yeah. As a case study example, I think when the HIV first appeared in the 1980s, it was still a rather rare and unknown disease. The tests weren't great. It was something like an 85% sensitive and an 80% specific, and the probability of the disease was about, well, less than 1% of the population. So given these numbers, this guy here would have been something like, I don't know, like 0.3 or whatever. So it meant you had the ridiculous situation whereby somebody would get a positive test result, but it means that they were more likely not to have the disease still. Which I know seems very strange. The test result is positive, so there's a 30% chance you have the disease. Right? Even with my example of 9999 and 1, it was a 50% chance. Yeah? So, just like the example I did with the kidney stones, I want you to see that even the simple level of probability is not as simple as maybe you might think. Yeah? Do you remember what the example was that you did with Colin when you talked about false positive and false negative?
We just took the definitions.
Just that's it?
Yeah.
It wasn't for a particular type of test?
Yeah, it was.
What is it?
You know those worksheets where he asks why do you do the consequences for you know those papers that you take and then he asks like, why do you test with only like ulcer and the or why do you test with only ulcer and the
No, that's okay. You heard of the terms false positive and false negative anyways. Yeah. Now, let's do one more example and then I'll let you work on these. Do you have that written down? Yeah. I can't remember, guys, but I think you have a similar effect going on when they look at DNA testing. You know, where they say something like, oh, we identified this person as being at the crime scene and the test is 99% sensitive. And, you know, it can be very easy to think that you're certain of the results when you start hearing numbers like 99% accurate and 99%, you know, and so on. But I hope you can see from this simple example that it can be more complicated than that. Okay. Now, we'll do one more example, interesting one here. Can I scroll down? Yeah. Yes? Right, so the last one here is, suppose you're on a game show and you're given the choice of 3 doors. So you have door A, B, and C. Behind one door is a car, but you don't know which. Behind the other 2 are goats. The booby prize. You pick a door. And the host who knows what's behind the door opens the other door, which is a goat. So just to give you an example, okay, let's say, for example, you pick A. And before the host reveals what's behind A, he'll open one of the other 2 doors and reveals the booby prize. So you pick A, and let's say he opens C, and he says, oh, C was the booby prize. And then he asks you, do you want to stick with your A? Or do you want to switch to the other door B? Do you know this game?
Yeah.
Yeah, so just for example, let's say you pick B, then the host will open one of the other doors, and he always opens a door to reveal the booby prize. Okay? He never opens the door that reveals that you didn't pick the prize, right? Your choice is, do you stick with the door you originally picked, or do you switch to the only other door that hasn't been revealed yet? Yeah? You see, most people are very stick with the choice that I made at the start. But let's see what happens in each case. So, you're right, we have 2 situations. we either pick we'll look at both. You either stick, you always stick, or you always change. Okay? So let's look at the probabilities here. Okay, so in situations where you stick, you have choice A, B, and C. Okay? Yeah. It's okay?
Yeah.
Yeah? Okay, so you have A, B, and C. Yeah, and one of these is going to be the winning one, isn't it? So maybe do I want to call them? Maybe actually rather than call them A, B, and C, we'll call it car or goat, yeah, or the other goat. Okay, fine. There's two goats. Right. So if you, this is actually a pretty straightforward calculation. If you stick with your choice, you got a 1 over 3, 1 over 3, 1 over 3. What is the probability that you will win the car if you just pick and stick and that's it? It's 1 over 3. I think you pick a door and you open the door and it's either the car or it's not. Okay, I'll give you a minute to think about this. What is the probability that you'll win the car if you always change your mind? So think about that for a second, see what you get. Try and draw the tree here. So I'll give you a little hint if it helps you. We kept this tree quite simple, but you could extend it a little bit more, okay? So for example, when you pick the car, although you don't know it's a car at the time, obviously, you have two choices, don't you? You can either stick or change. Now in the case of you pick the car, if you stick with it, then you win the car. No, remember in stick situations you always stick. So this is a 1 and this is a 0. Here, win, lose. If you, what are we doing? We're sticking. So actually, yeah, so you're guaranteed to lose here, isn't it? And then here, you're sticking, so you're guaranteed to lose here, aren't you? 1, 0. So in this situation, it looks a little bit different. Let's see. Car, goat, goat. Still 1 over 3, 1 over 3, 1 over 3. Okay, if you pick the car and you change your mind, do you win or lose? You lose. And you always change your mind, so here that's a 1 and that's a 0. Okay. Here, win, lose. You pick the goat and you change your mind, do you always win or lose here? Win, because there's only one other door which has to be the car because the host revealed the goat. And then here, win, lose. If you change your mind again when you pick the goat, you're guaranteed to win. So let's calculate the probability of getting that car, of winning. So first one is 1 over 3 times 0 plus, yeah, no, not going to happen, plus 1 over 3 times 1 plus 1 over 3 times 1, which equals 2 over 3. You are twice as likely to win if you always change. So it doesn't matter. In this game show, the best thing to do is always change your mind. And doing so would make you twice as likely to win the car than if you always stick. So your intuition to always stick, which is what most people do, is you're cutting your chances in half of winning the car. Okay? Now, why did you think to always stick? Because it's psychological. Because the choice you make seems like the right choice at the time. So you shouldn't doubt that. But here it's an example where you should always change. Yeah? Yeah? And I've got another question here to make you really think about this. So, in this, imagine you've made your choice. So you've got A, B, C, and you pick B. Okay? And your choice is, do you stick with B, or do you opt for C? Right? One of these is a winner, and one of these is a loser. So if I said to you, here are two choices. The first choice, doesn't matter what it is, you could win. The second choice, you could lose. You make the right choice, you win. The wrong choice, you lose. That's a little bit like flipping a coin, isn't it? Right? Like if I had two hands here, one of them's a winner and one of them's a loser, what's your chance of picking the winner? 1/2. It doesn't matter that earlier I said you pick this hand and then later I say, do you want to keep with this hand or change it? It still should be 1/2, equal. It's not 1/2. What do we calculate it as? 2/3. Which also seems surprising, because it seems like it should be 1/2, right?
Yeah.
But it's not.
Yeah. Because
Yeah.
in the first case, we used to open certain doors, so we know that.
Yeah, you open the door and you know
You
there's
don't have
a goat
certain
in there.
hands, Yeah.
Yeah. So how many doors are left?
Two.
Two. One is a winner and one's a loser. If you stick or change your mind, it should seem like it's a 50-50 chance of winning.
No. Yeah. Oh my goodness.
There's two doors, yeah. One of them's a winning door, or there's a losing door.
Because you know that the third one is not.
The third one's out of the game at this point. So your choices are, do you pick the other door or do you stick with the door you have? You've got a 50-50 chance, it would look like.
But with the hands, you have only two hands. You don't have third hands, so you can open.
But the third.
But once you open the door, you don't get what I'm saying. How can I demonstrate this?
So I think in the end there are only two options.
There's only two options. Do you stick or do you switch? And you have two doors at the end. And one of them's a winner and one of them's a loser.
Yeah.
So it seems like it should be 50-50.
So, but it's actually not.
It's 2/3.
Yeah.
Yeah.
Why?
Yeah, but we just calculated it. You're not happy with this?
It's kind of
No?
confusing.
Right, look.
It's confusing.
Okay, Dasha, pick a door.
B.
B, okay. So you're sticking with B, so that's your choice, okay? I open A and I see that there's a goat behind it. Okay, fine. So A is out of the game. Right. Would you like door B or would you like door C?
Door C.
Okay, what's your chances of winning if you make this decision?
2/3.
Correct. But it seems like it should be 50-50, no?
No.
But you have two doors here.
Complain with that. Yeah. Okay. Yeah.
Let me simplify it. I have two doors. One's a win and one's a lose. Which one do you want? A or B? Say A.
A.
What's your chance of winning?
50.
50-50. Now, how is that situation anywhere different to this situation where I say, do you want to stick with B or switch with C? It's like me saying, do you want B or do you want C? Do you want the choice B or do you want the choice C? And one's a winner and one's a loser. So it seems like at this point it's 50-50.
Yeah.
Yeah, but it's not.
Yeah.
That's what I'm saying.
Yeah.
Yeah, because three doors
We have a previous history about it.
Yes. You're right. This is what makes it different. There is, it's not like the game has only begun at this step.
Mm-hmm.
That's the key difference between that and say this game here. This, what's it called? It's a famous example because it's named after a real TV game show that did this. No, Monte Carlo or something. Like this.
I saw the same idea on YouTube.
Did you?
Yeah.
Where you stick or switch,
Yeah.
and you have a choice of three. Yeah. Okay.
No, I saw the video. Like I saw the video you told.
Yeah. Yeah.
Why?
What video?
I just remember it said 4 long time ago.
And then
Are you finding
your
the video?
A or B, then they switch the price.
He's finding the
So you will not get it. You get it. Then what about that?
Anyways, it's just an interesting example here. I can't remember. Oh, this was a famous example because it was in some magazine like years and years ago, and it was the most people wrote in to complain about this question in the magazine than any other thing in the magazine ever, because most people would not accept that the answer was 2/3. You know, they would not accept that it was 2/3.
There was this question in a magazine.
Yeah, you know the way like you have riddles or puzzles in newspapers or something.
Oh.
So the question, like they had the story and they said, what is the chance of winning if you always change your mind? So most people would not accept that it wasn't 50%, that it was 67%.
Yeah.
You know? So they were saying that this puzzle generated the most letters of complaint to the newspaper than anything else in the newspaper ever. Okay, right. So what I'd like you to do, if you could do 1 to 7 as a minimum, but if you want to try harder ones like this one, they're 8 to 12. Now, what time are we at? Okay. So we have class tomorrow.
First
We're going to start our revision tomorrow. I want to look at section B, I think, because we're going to be making the section A database on Friday. So if you want to bring your laptop, because we'll be looking at exams on Moodle. Tomorrow, yeah. Where are you heading off to now? Are you finished? Finished?
Why?
She just said that she's here.